Huh. Hey. Good question. Let's talk about that. So, this is a fractal. This is also a fractal. This is what I made. This is also a fractal. A fractal, according to Google, is a curve or geometric figure, each part of which has the same statistical character as the whole. Fractals are used in modeling structures such as eroded coastlines and snowflakes, in which similar patterns recur at progressively smaller and smaller scales. In describing partly random or chaotic phenomena such as crystal growth, fluid turbulence, and galaxy formation. These fractals that I have been showing you are mathematical concepts. This first one that I showed you is a Sierpinski carpet. It has a three-dimensional version, which is a Sierpinski sponge or a Menger sponge. And these are quite simply formed. You take a square or a cube. You divide the square up into 9 pieces, a 3x3 grid, or in case of the cube, a 27, divided into 27 pieces. You then remove the center square of the carpet, or the middle faces and the center cube for the Menger sponge. And then each of those is then itself a Sierpinski carpet, a Menger sponge, depending on your dimensions. So you eventually get this very wholly image, which is a fractal. It is recursive. It is defined by itself, and you can also do this for other shapes, like an equilateral triangle, and you get a Sierpinski triangle. This second fractal that I showed you is called the Koch snowflake. It is a fractal that starts with an equilateral triangle, and then the middle third of every line segment then gets a, 2 line segments to then form another equilateral triangle, and you eventually get this thing that looks quite like a snowflake. What I have made is called the Mandelbrot set, or a Mandelbrot fractal. This is also recursively calculated and requires some knowledge of the imaginary plane. So, conceptually, you can have a number line, and then you can have a number line that goes perpendicular to that, which is the imaginary line. So you can write any coordinate on that page, on that grid, any point can be written as a combination of a real part and an imaginary part. For our purposes, we will actually need to know what the imaginary number is. The imaginary number is the square root of -1. And then, now that we have this concept of the imaginary plane, we can look at how to create a Mandelbrot. The Mandelbrot set is defined for every point on the imaginary plane as this formula. And we'll break down each of these parts, don't worry. So, this part, this C, is simply the point that we are looking at. So, this is x plus y times the imaginary number. Z is what we recurse on. So for your standard Mandelbrot set, we start out with Z being 0. And then for the next step, we look at, for the first step, the formula is z squared, so 0 plus 0i squared, which is 0, plus the point we are looking at, x plus yi. Fairly simple. The next step would then be that x plus yi squared plus x plus yi, and so on into abstraction. The Mandelbrot set is defined as the set of points whose central tendencies do not diverge from 0, 0. So, if we take a point, very far away from 0, 0, in fact, if we take a point outside of a radius 2 circle, a circle with radius 2, the length of the distance from the point after an infinite number of recursions to 0 is going to be massive. A point outside of a circle of radius 2 is going to diverge very quickly. Within a circle of radius 2, things start to get a little bit more interesting, because on the negative side of the real numbers, we'll not be looking at imaginary numbers right now, at -2, right? We can look, and the recursion is as such. We start at 0, 0. The first step is 0 squared plus -2, so that's -2. The second step is -2 squared which is 4 minus 2, which is 2, squared, right? For the next step, that would be 2 squared, which is 4, minus 2, which is 2, and so on. So we never actually diverge at the point -2. And yeah, that is a basic overview of the Mandelbrot set and how this is defined. Now, we're going to get a little bit more in depth about this with some programs that I've written previous to this. Okay, welcome to an example. This is going to be a little bit interesting because my mouse doesn't completely line up with the recording, but I can try and look at the recording and figure out what's going on so I can actually point to things. So here we have just your normal imaginary plane, right? We have a real number line going across and a imaginary number line going up. Except for the fact that we have negative i's on top. And we're back. What we have here is the imaginary plane, right? We have a real number line going across, an imaginary number line going up and down. Okay. So, right now, this program is graphing, every point with recursion depth 0. So no point has been able to fail, because at every single point on this map, the recursion depth is stopped at 0, so the function is at 0, 0. So we don't really, no point has diverged from 0 yet. If we press the 9 key, because I mapped it to 9 for whatever reason, we go to the first recursion depth. And now we can see that every point outside of this circle has broken out of the loop, has diverged. Because there's a mathematical proof that once a point, once a recursion depth has gotten further away from 0 than 2, you're not going to be able to get that point back then. Because, I did my example for -2. Let's look at -3 now. -3, first recursion is 0. Zeroth recursion is 0. First recursion is 0 squared. -3 is -3. -3 squared is 9. -3 is 6. Squared is 36. -3 is 33. Squared is a big number. And thus, we cannot, -3 is going to diverge from 0 quite a bit in that direction. Same for other points outside here. So like 3i squared is -9, right? So it's all the way over in that direction. -9 squared is wait, no. Zero, 3i, -9 plus 3i. So that way and up to 3i. And then a squared plus b squared. So 81 plus 3 plus 9. 81 plus 9 is 90. And then -2. It's all the way over here in 90. And then 2ab is 2. 3 times 9 is 27. So that's it's over at 80. 27i, -27i. I might have dropped a negative in there somewhere. It's diverged. Similarly, if we go to the next recursion depth, which is interesting, you can see that quite a lot of this circle of radius 2 has now broken out. Most importantly, and most easily to describe, is the point 1. There, 1. So, let's do the recursion on that. 0th recursion is 0. 0 squared plus 1 is 1. 1 squared plus 1 is 2. 2 squared is 4, plus 1 is 5. 25 plus 1 is 6. Is 26. 26 squared is going to diverge from 0. And then we can continue going one recursion depth more. There's not particularly a good explanation, like a good example point at this recursion. Is that like 0.5? Let's see, 0.5, 0.25, 0.75. That's probably going to diverge eventually, so that we might have just lost 0.5. I should really have just set up like an Excel sheet. So it appears that so that's first recursion depth, second recursion depth, third recursion depth. We're going to lose 0.5 here in a little bit in 2 more recursions by the looks of it. I just set up a little Excel thing so I can actually calculate these things. So let's actually move forward, because I mean some of these points there's not really good example points for. So let us do that, because I believe that somewhere in the blue area, there we go, we have just lost 0.5, because let's do the recursions here. 0th recursion is 0. First recursion is 0.5. 0 squared plus 0.5 is 0.5. 0.5 squared is 0.25. plus 0.5 is 0.75. 0.75 squared is 0.5625. Plus 0.5 is 1.0625. 1.0625 squared is 1.12890625, I would assume. Plus 0.5 is 1.6289. Squared is 3.15333. 10.44, 109. It's broken out. Yeah, and we can actually see that as I continue adding more and more recursions, we slowly start to approach what we had. Sorry about the epilepsy. What we had in the video. I don't remember what my center color was. It was pink. Whatever. Let's do orange. That's fine. Yeah. So that is how recursion on the Mandelbrot set works. And we can prove that this function doesn't just completely collapse on itself. Because, I mean, we were able to show that -2 never breaks out. Because it goes, 4 minus 2 is 2 squared minus 2 squared minus 2 squared minus 2. That -2 is part of the Mandelbrot set. 0 plus 0i is also in the Mandelbrot set because that will never diverge from 0 because it will always be 0. -1 is also quite an interesting thing because zeroth recursion is 0. First recursion is -1. Second recursion is -1 squared, which is 1, minus 1, which is 0. And then we just repeat now. So it goes 0, -1, 0, -1, 0, -1. Pretty nifty. I can pull up Excel thing to do other points. But let us, instead of me just calculating things in Excel and then telling you about them, let me switch over to my other program to better illustrate what I am talking about with this concept of diversion.